in this video, we'll start by talking about elementary symmetric functions and computing the Galois group of a certain extension of function fields. And the main idea in this video is to set up the discussion of the discriminant of a polynomial that will happen in the next video. Okay, so let's start by just saying that x1 up through xn are going to be indeterminants. So there are a bunch of variables. There's no polynomial relations between them. You should think about like, what are the different x1 through xn when you consider a polynomial ring in a bunch of variables. So given these indeterminants, we'll define the elementary symmetric functions, s1 up through sn. And they'll be defined by s1 is just a sum, x1 plus x2 plus xn. And s2 will be the sum taken two at a time, x1 times x2 plus x1 times x3 plus x1 times xn, and then plus x2 plus x3 plus x2 plus x4 plus x2 plus xn, and then on and on and on, xn minus 1 times xn. So you could write this much more simply as a sum where you go over all pairs I less than j of xi times xj. Similar S3, S4 up through Sn, which is the sum of the product of all n of these, x1 times xn. So what is Si? It's the sum of all products of the xj taken I at a time. And you can give every one of these a nice expression that looks like this one. Okay, so we're going to define for any field f, the general polynomial of degree n over f. This is going to be a polynomial whose roots are these indeterminates, x1 up through xn. So it's it's x minus x1 times x minus x2 times x minus xn. So it's a polynomial in the single variable x, and we know its roots are x1 up through xn. And it's a little induction exercise to show what happens when you expand all of these terms out. Is the coefficients are described very nicely as plus or minus these elementary symmetric functions in these x1 up through xn. So we get xn minus s1 times x to the n minus 1 plus s2 times x to the n minus 2 minus s3 times x to the n minus 3 plus minus 1 to the n times sn. Okay, so you can prove this by induction, and it's worth working it out once. So what is this thing? This general polynomial of degree n over f. This is an element of f adjoin s1 up through sn bracket x. So it's a polynomial in x whose coefficients are in the field generated over f by these elementary symmetric functions, s1 up through sn. Okay, so this polynomial is separable. These roots, x1, x2 up through xn, are distinct. I mean, even more than being distinct, there's no polynomial relations among these roots. So if you take this field, f adjoin s1 up through sn, and you adjoin x1 up through xn, then in fact, because every one of these elementary symmetric functions can be described as in terms of x1 up through xn, if you take f and you adjoin x1 up through xn, you also contain s1 up through sn, right? Like these symmetric functions are just combinations of these xi's. So what we're seeing is that the field generated over f by x1 up through xn is the splitting field over the field generated over f by s1 up through sn of the general polynomial of degree n. We've defined this polynomial so that we know its roots. Okay, so what does that mean? We have these two fields, and we have this extension of these fields, and we know that the first field is the splitting field of a separable polynomial with coefficients in the smaller field of degree n. So the degree of this extension divides n factorial. So in particular, it's less than or equal to n factorial. Okay, so what do we want to know? We know that we have this extension of degree at most n factorial. We know that it's a Galois extension because it's the splitting field of a separable polynomial. What is the Galois group of this extension? And I'll pause and erase, and we'll show that it is all of Sn. So let me just say, this kind of extension is not something we have talked about very much. And I find the presentation in this little section of Dumbit and Foot to be a little bit confusing because we have not talked a lot about these kinds of extensions. So I'm going to go a little bit quickly and not really emphasize the details here. What I want you to understand is the big idea about what extensions like this tell us about computing the Galois group of, say, low degree polynomials with coefficients in Q. We want to understand the extension given by f adjoin x1 up through xn over f adjoin s1 up through sn. Okay, so we want to think about automorphisms of the field generated over f by x1 up through xn. Any permutation, sigma and Sn, acts on this field by permuting these xi's. And it's true that every such sigma gives an automorphism of this field. Okay, so there's something to check there, and you really should check it, but it's straightforward to prove. So now we can take our element sigma and Sn and identify it with this automorphism of f adjoin x1 up through xn. What does that give us? Well, it's clear that different sigma give different automorphisms. We can see that this identifies Sn as a subgroup of the group of automorphisms of f adjoin x1 up through xn. Okay, so now we want to understand this group of automorphisms. So proposition 30 in section 14.6 says that the fixed field of Sn acting on f adjoin x1 up through xn is f adjoin s1 up through Sn. Okay, so how to think about that? Sn acting on this group is we're identifying Sn with this particular subgroup of the group of automorphisms of this field. So we have a finite subgroup of automorphisms of a field, and we can say, what is the fixed field of that subgroup of automorphisms? So what is the subfield of f adjoin x1 up through xn, consisting of elements fixed by every element of this finite group of automorphisms? And we're going to see that that is the field generated over f by s1 up through sn. Okay, so let's prove this. If you just look at how the elementary symmetric functions are defined, each one of these is fixed under any permutation of the xi's. So what does that mean? That means that any permutation of the xi's, you take your permutation, you get this automorphism of f adjoin x1 up through xn. S1 up through Sn, those are all fixed by any one of those automorphisms. So the whole field generated over f by S1 up through Sn is fixed by every one of those automorphisms, because S1, S2 up through Sn, those are all fixed. F is certainly fixed. So this field is contained in the fixed field of Sn acting on f adjoin x1 up through xn. Okay, so these automorphisms of f adjoin x1 up through xn, they're not just automorphisms, they are automorphisms of f adjoin x1 up through xn fixing f adjoin s1 up through sn. We're not saying that's the whole fixed field, but it's certainly contained in the fixed field. So any one of these automorphisms does fix this field. And we know that f adjoin x1 up through xn gives a Galois extension of f adjoin s1 up through sn because it's the splitting field of a separable polynomial. So now we can apply the fundamental theorem of Galois theory and say whatever this fixed field is, it has index n factorial in the field f adjoin x1 up through xn. So we know the index of the fixed field because we know the size of this group. So Sn is this subgroup of size n factorial. So the index of the corresponding fixed field is n factorial. But we know this field, f adjoin S1 up through Sn, which is contained in this fixed field. And now, since we know that the index of f adjoin S1 up through Sn inside of f adjoin x1 up through xn is at most n factorial. We said this earlier because it's a splitting field of a degree n polynomial. Okay, so this field is contained in the fixed field. The fixed field could be bigger, which would make the index of the fixed field smaller. Bigger field, smaller index, smaller degree of this extension, I guess is a better way to say it. Because we know that the index of the fixed field inside of the degree of f adjoin x1 up through xn over this fixed field that we're looking for is n factorial, that means that in fact, this degree must be equal to n factorial, and the fixed field is the field generated over f by S1 up through Sn. Okay, so that's the end of that proof. This has a really nice consequence. A rational function, f in x1 up through xn, is called symmetric if it is not changed by any permutation of the xi's. So you permute the xi's however you want, and you get back the same rational function, then it's called symmetric. Corollary 31 is the fundamental theorem of symmetric functions, which says that any symmetric function in x1 up through xn is a rational function in the elementary symmetric functions s1 up through Sn. So this is part of why they're called the elementary symmetric functions. How does the proof go? A symmetric function in x1 up through xn is an element of the field f adjoin x1 up through xn that is fixed by Sn, by all these automorphisms of this field that come from permuting the xi's. So it has to lie in the fixed field of this action, f adjoin S1 up through Sn. Okay, so now the last thing to note is that what is the field generated over f by S1 up through Sn? It is consists of rational functions in these elementary symmetric functions S1 up through Sn with coefficients in f. And now let me say, if I'm being really honest, I don't think that Dummett and Foote ever really clearly explain how to think about what the elements of this field look like, that they are rational functions in S1 up through Sn. So I'm going to leave that aside for now. We're not going to need to think very hard about that. I want to note that something better than this is actually true. So I'll pause and erase, and I'll talk about the fundamental theorem, not of symmetric functions, but of symmetric polynomials. And then we'll see another way to think about this whole picture involving this extension, f adjoin x1 up through xn over f adjoin s1 up through Sn. We've talked about the fundamental theorem of symmetric functions. Let's talk about the fundamental theorem of symmetric polynomials. We know that any symmetric rational function in x1 up through xn is a symmetric rational function in S1 up through Sn, is a rational function in S1 up through Sn. What if your symmetric rational function in x1 up through xn is actually a polynomial? Any symmetric polynomial in x1 up through xn is a polynomial in S1 up through Sn. Okay, so Dummett and Foote don't prove this in the text, but in exercises 37 to 43 in section 14.6, they give this extended discussion about how to take a symmetric rational function in x1 up through xn and express it in terms of S1 up through Sn. And you see through this process that when your rational function is actually a polynomial, what you get out is a polynomial. So I'll point out that this is sort of a side direction that plays an important role in section 14.6, but symmetric functions and symmetric polynomials is not Dummett and Foote's main topic at this point. When I was in graduate school, I took this really awesome course that was all about symmetric functions using part of Enumerative Combinatorics Volume 2 by Richard Stanley. I'll just point out that this is a really rich and beautiful subject that has all sorts of connections between algebra and also combinatorics and other fields too. So this is something that's really interesting that I encourage you to read more about in the future. Okay, so what are we going to do now? What have we done so far? We started with a field f, and we talked about the general polynomial of degree n over f. This was this polynomial that we defined in terms of its roots, x1 up through xn, being these indeterminants. And then we saw that you could think of this polynomial as being in f adjoin s1 up through sn, where these si's are elementary symmetric functions in these roots, x1 up through xn. So it's a little weird because we started with this field f adjoin x1 up through xn. We started with these roots, and then we made a polynomial out of them, and we asked where do the coefficients live, and we found this subfield f adjoin s1 up through sn. Almost all the time, we've started with a field, and then we've built field extensions from that field. Rather than going from the top down, we go from the bottom up. So what I want to do now is talk about what happens when we start with a polynomial with coefficients in a particular place and try to understand what happens when we adjoin the roots of this general polynomial. Okay, so that's the idea. So suppose we start with the general polynomial defined in terms of its coefficients. Let's say x to the n minus s1 x to the n minus 1 plus s2 x to the n minus 2 minus s3 times x to the n minus 3 plus minus 1 to the n times s to the n, where what are these si's? Now, clear your mind. They are just independent indeterminants. So don't think of them as symmetric, elementary symmetric functions yet. So these are just indeterminants. So what does that mean? So one thing that means is that there are no polynomial relations among these si's. So if you have a polynomial p in t1 up through tn with coefficients in f, such that p of s1 up through sn equals 0, then the polynomial equals 0. So, okay, so what does that mean? So think about this polynomial as an element of f adjoin s1 up through sn bracket x. So it's a polynomial in the single variable x whose coefficients are, I mean, they involve these s1 up through sn. Certainly they're in the field generated over f by s1 up through sn. Okay, so this polynomial, it has n roots in a splitting field, not necessarily distinct. So let's name those roots. So where do the roots come from? We know there are n roots in a splitting field. We're just going to name them. So let's call them x1 up through xn. So what's going on here? We start with this polynomial whose coefficients are given in this way. And there's no relation between these coefficients. We name the roots. And now when we multiply out x minus x1 times x minus x2 and so on, we see that if with these names for the roots, these si's are exactly the elementary symmetric functions in these xi's, in these roots. So what has happened is now, instead of starting with the roots of a polynomial and asking what are the coefficients and using that to define this field f adjoin s1 up through sn, we're just starting with this polynomial whose coefficients are these indeterminants, plus or minus. We name the roots, which we know exist somewhere, and we see that these si's have this interpretation in terms of these roots. Okay, so what does that give us? Since there are no polynomial relations among these si's, we'll see that there are no polynomial relations among these roots either. Why is that? So if you have this polynomial in these variables t1 up through tn, coefficients are in f, and this is a non-zero polynomial where you put in x1 up through xn and you get 0. So you have a polynomial relation with coefficients in f satisfied by these roots. Then, okay, I don't really know anything about this polynomial. But if you take the product over all sigma in Sn of p, but now you permute t1 up through tn by sigma, so you take p of t sigma 1, t sigma 2 up to t sigma n, when you take the product over all of these sigma, what you get is something that is symmetric. So it's now a symmetric polynomial. And when you plug in x1 up through xn for t1 up through tn, because one of the terms in this product is 0, the one that comes from the identity permutation, you have this symmetric polynomial where you put in x1 up through xn and you get 0. And this gives us a non-zero polynomial relation among s1 up through sn. Why? Well, this is a non-zero symmetric function in x1 up through xn, so it is a rational function in s1 up through sn. And now you have a rational function that's equal to 0. The numerator of that rational function has to be 0, which gives a polynomial relation among s1 up through sn, which is not possible because these si's, s1 up through sn, are indeterminates. So this gives us a contradiction. So let me point out that I feel like this is also a place where this style of argument feels very unfamiliar because we haven't been talking about field extensions involving a bunch of independent indeterminates. So I want to give you the big ideas, but I wouldn't worry about this kind of argument too much right now. Okay, so I'll pause and erase, and we'll talk about this extension. We have now f adjoin s1 up through sn, and we can adjoin the roots of this polynomial. So we can take this field and adjoin x1 up through xn. Okay, where are we? We started with this polynomial, this general polynomial whose coefficients were these independent indeterminates s1 up through sn with plus or minus 1s multiplied by them. And we saw that if we name the roots x1 up through xn, then now these si's are exactly the elementary symmetric functions in these roots, xi's. And we saw that if the si's have no polynomial relations among them, the same is true for these roots xi's. Okay, so when we started the other way and we defined this general polynomial in terms of these roots, we got these elementary symmetric functions, s1 up through sn, defining our coefficients. And Dummin and Foote just make this comment that conversely, if the roots of a polynomial f of x are independent indeterminates over f, then so are the coefficients of f of x. And to really make this precise exactly what is meant here, it's helpful to see some of the material that's coming up. So they just cite this forward to section 14.9. But what's the take home of this discussion is that defining the general polynomial over f in terms of having independent roots, the first thing we did, x minus x1 times x minus x2 times x minus xn, where x1 up through xn are independent indeterminates over f, or defining the general polynomial as having these independent indeterminate coefficients given in terms of x to the n minus s1 x to the n minus 1 plus minus 1 to the n sn. This leads to something equivalent. So in the first case, we saw that f adjoin x1 up through xn over f adjoin s1 up through sn is a Galois extension with Galois group, the full symmetric group Sn. And if you start by defining the general polynomial in terms of these coefficients, and then you adjoin all these roots, you get the same thing. You get Theorem 32 in section 14.6, which says that the general polynomial x to the n minus s1 x to the n minus 1 minus s2 x to the, or sorry, plus s2 x to the n minus 2 plus minus 1 to the n s to the n sn is separable with Galois group Sn. Okay, so how to think about this? What this is saying is, what are we requiring of s1 up through Sn? That they're indeterminates over f. So if there are no relations among the coefficients of a polynomial of degree n, the Galois group over the field generated by its coefficients is Sn, the full symmetric group. Okay, so let me point out a comment that Dummin and Foote make, which is true, that you can use this idea to show that most degree n polynomials with coefficients in Q are separable with Galois group Sn. So you just have to show that most degree n polynomials, with most defined in some precise way, satisfy this no relations requirement that you need. Okay, so there's something certainly to do here, but this is true. I will point out you have to be careful about this no relations statement. For example, if you replace Q with a finite field, every finite extension of FP is cyclic. So it's just not true, once n is bigger than 2, that most degree n polynomials in FP bracket x have Galois group Sn. I mean, none of them do. So what's different here is that the coefficients of a polynomial in FP bracket x satisfy lots of relations. The finiteness forces them to, and the same thing is not true over Q. Okay, so what is this whole video about? Is we have, starting from this general polynomial over f, when you take the splitting field of this general polynomial, you get a Galois extension of f adjoin S1 up through Sn, whose Galois group is the full symmetric group Sn. So now we can use the Galois correspondence to say interesting things about extensions of f adjoin S1 up through Sn that are going to have actual concrete consequences for polynomials of low degree over Q. So in the next video, what we'll focus on is the discriminant of a polynomial and what that tells us about its Galois group. So let me just say, I find this discussion in Dummett and Foote really to be a little bit confusing. It's a place where I like the Galois theory presentation in Dummett and Foote a little bit less. It gets better if you go forward and you read some of this stuff about from the beginning of section 14.9. So you should understand the big idea and the consequences that come out of this, but I am not going to ask you to prove anything from this video on the final exam for this course.